so I think for nomenclature, the maximum amount of practice you can do is best. So this is why I went through every single problem in the chapter. That way you see as many examples as possible. And so that's what the 2 videos on YouTube are about. But we talked about the rules for naming these things, and then they had these strange rules for naming acids, which I skipped that. And, at the very end of this, we have some hydrates. Okay, I guess we're okay. So we did cover everything. I talked about hydrates in the video. I gave some examples of hydrates as well. We'll see those as we go along. So take a look at that. But essentially, you should have every single problem done in the homework because I'm just going through them with you guys. It's just so you get more practice. It's not that hard for chapter 6. So we're done with chapter 6. We'll move on to chapter 7. I'm going to post another video going through the remaining problems in the book. Chapter 7 deals with chemical formula relationship. In other words, a chemical formula tells us the composition. It tells us the composition by atom or but that's not the only way to tell us the composition. There are 2 very common ways to determine the composition. What's the composition of anything? The 2 most common ways are percent by mass, or mass ratio. So percent by mass, let's look at water. If we consider water, what is the composition of water? Composition of water is H2O. But, this composition, this is the atom composition. By mass, we know that the average hydrogen atom weighs, where can I find the average weight of a hydrogen atom? The average weight of a hydrogen atom. Off the periodic table. And so if we look at the periodic table is going to average out the masses. Now, for hydrogen, there are 2 masses. Hydrogen is a very common element, and so since hydrogen is very common, sometimes we like to remember these to 2 decimal places or to 3 decimal places. Of course, we could get 6 plus decimal places, but we're not going to calculate everything to 6. Most commonly, we're going to calculate it to 2. And so we use this when hydrogen is in a compound. When H is in a compound. And then we use this for elemental. Elemental will be H, which would be atomic hydrogen, which would be 1.008 U per atom. Or elemental would be H2. And the average hydrogen molecule is 1.016 U per molecule. So if I have a single molecule of H2, it's 1.016. A single atom of hydrogen is 1.008. The reason we do this is to give us 4 sig figs. 4 sig figs. But if I look at water, O is easy. It's 16.002 decimals. So we can remember that. And so for H2O, I have 2 hydrogens. 2 hydrogens is going to be 2 times 1.01 U, which gives us 2.02 U. And then we have 1 oxygen. 1 oxygen is 1 times 16.00 U. And that's going to give us 16.00 U. Now when I do the addition, because the rules for sig figs, I'm allowed, how many sig figs am I allowed here? the final sum? Well, that's a trick question because it's not sig figs that I care about. What is it that I care about? I care about the decimal places. And so I'm allowed 2 decimal places here. So this is going to come out to 18.02 U, which is how many? That's 4 sig figs, 2 decimal places. And so this is why in compounds everything's heavier than hydrogen. Hydrogen's the lightest. And so when we put hydrogen in a compound and we carry 2 decimal places, we have 4 sig figs in our final mass. And so this would be the weight of water. And so 1 water molecule would be 18.02 U per molecule. Now this is the average weight of a water molecule. In nature, we aren't going to find a water molecule that weighs this. Why? Because this is the average of all the isotopes. And if we get a specific molecule in nature, it's going to consist of very specific isotopes. For example, H1, O16, H1, which is slightly different mass here. And the same thing goes for hydrogen. We aren't going to find a hydrogen molecule in nature that weighs this because this is the average of water molecules found in nature. Now, if we do percent by mass composition, percent by mass is just equal to the mass of A over the total mass, whatever A is times 100%. And so if we want this is percent by mass of A. If we want the percent by mass hydrogen, we could figure it out. So let's do percent by mass hydrogen. I'll do percent hydrogen by mass. Sometimes this is written like this, so there's no confusion. This is called a percent M over M. M over M is the mass of A over the total mass, or percent WW, W over W. This would be the weight of A over the total weight. And so if we're looking at the percent by mass for hydrogen and water, it would be the mass of hydrogen. Well, what is the mass of hydrogen and water? The total mass of hydrogen alone is 2.02, since we have 2 of them. So we'll just go with that. Or the alternative is if we want to keep 4 sig figs, then maybe we should use this times 2. We're not going to use this because this is for H2 molecules, but 2 hydrogen atoms weighing 1.008 U. It's 2 hydrogen atoms. That gives us the 4 sig figs. Over here, because of this addition, we'll end up with the 4 sig figs. But over here, I'm going to use this. Over the total mass, what is the total mass? And so this is of the hydrogen. The total mass is going to be 18.02 U total for the H2O times 100%. And so we can calculate it. So about 2 out of 18 grams will be hydrogen. What is the percentage? Around 10%. So 2 times 1.008 divided by 1802. 1802 times 100. And so I get 11.87. 187% hydrogen. By mass. Well, there are only 2 things in here. So if it's about 11% hydrogen, it's got to be about 89% oxygen, because the oxygen is the remaining. And so there are 2 ways we can calculate percent oxygen. Percent oxygen we could do by A. There's 100% minus 11.187%. Now, how many sig figs are in 100%? Infinite, actually. And so this this is going to be limited to 2 decimals, so it's going to be 88.813% oxygen. Or B, alternatively, I can just do it like this, percent, using the same formula, percent oxygen by mass is equal to the weight of the oxygen. The weight of the oxygen is 16.00 U. So that's how much oxygen we have over the total weight of 18.02 U times 100%. The U's are going to cancel. The oxygen and the water, but that's what we're after. And so let's calculate it. It's going to be 16 times 100 divided by 1802. 88. Oh, I must have made a mistake in my calculation over here. 88.790%. So this is 88 point, I better do this rather than, my math is not so good. 11.813. 88.18, sorry, 88.187. Oops, that can't be. I must have miskeyed it just one second. 100 minus 11.187. 88.813. Okay, 88.813%. Now, the situation is the percent hydrogen plus the percent oxygen has to equal 100% because this is just made up of hydrogen and oxygen. And so if I take 11.187 plus 88.813, that equals 100%. However, if I take 11.187 plus 88.79, do I get 100%? So let's try this one. 11.187 plus 88.79 equals, I get 99.977%. Do you see that? It doesn't add up to 100%. There's a little bit, there's like 0.003% missing, or 0.03% missing. What do you think that's attributable to? Round off error. Basically round off error. I should have carried lots of digits here, and then those two numbers would add up to 100%. So you have to be careful. Sometimes these errors are due to round off, sometimes the errors are due to a miscalculation. If the error is big, then likely it's miscalculated. If the error is small, it could be just rounding error. Because do you see that this one plus this one does not add up to 100%? And so now we get the composition of water. What is the composition of water? Well, if we want the composition of water, did you know this? Water is 11 point, let's just go ahead and round it again. Water is 11.19% hydrogen and 88 point, okay, we'll round this one too, 88.81% oxygen. That's what we have. So, but you know, when we think about it, this is by mass. But when we think about water, there are 2 hydrogens for every oxygen. And so we can also do percent by atom. If we do percent by atom, then we have H2O. If we have H2O, then how much hydrogen is there? And so percent by atom would just be like this. Percent atom of A, which would just be atoms of A over total atoms times 100%. And so if I'm doing percent hydrogen, by atom, this is going to equal 2 hydrogen atoms for every, how many total atoms are there in water? 3. And so 3 atoms total times 100%. And so what that gives us is 2/3 would be 66.6. We're allowed 4 figs, I think. 66, or actually, we're allowed more than that for this. So just keep going. About 66.7%, 66.67%, or if you want to round it, hydrogen. Okay, this is by atom. And so, it's just because these hydrogen, and even though there's more hydrogen atoms, do the hydrogen atoms weigh very much? No, hydrogen atoms don't weigh much. Hydrogen atoms weigh about 1 U. Oxygen atoms are 16 times heavier than hydrogen atoms. And so this is why when we look at it by atom, it's definitely mostly hydrogen, but when we look at it by mass, it's definitely mostly oxygen. Okay, so then that means the percent oxygen, we could do the same thing, 100 minus that, it's going to give us 33.33, etc. percent oxygen by atom. Well, we can do the same calculations. This is going to be 1/3 times 100%. All right, so we have percent by mass, we have percent by atom, and then we have atom ratios. Atom ratio is just, how everybody, when anybody asks what's the composition of water, they always give the atom ratio. The atom ratio is 2 atoms of hydrogen for every atom of oxygen, H2O. The atom ratio, or the chemical formula. We could do other ratios too. The other ratios would be a mass ratio. A mass ratio would be H 11.19, O 88.81. So if somebody asks you, hey, what's the composition of water? You'd say H 11.19, O 88.81. Is doing a mass ratio very convenient? Is it an easy number to remember? No. And so mass ratio, this is the mass ratio. Mass ratios are not so useful, but we can easily get the mass ratio. And so for expressing the composition, the two most common, of course, are going to be the atom ratio, which is just the chemical formula, and the percent by mass. And so the two most common ways of doing this, but you don't have to restrict yourself, of course. The two most common would be the atom ratio. This is for composition. Expressing composition would be atom ratio and percent by mass. Well, we like the atom ratios because they just tell us how many atoms of each. When you look at this, the mass ratio, can you tell me how many atoms of each? No, it's very difficult. And so this is what chapter 7 is about, chemical formula relationships. So these are chemical formulas, atom ratio. But we're going to relate it to different things. And also we're going to start looking at chemical properties as well. In other words, chemical reactions. So these are the learning objectives. So the first thing here in this chapter is writing the formula of a substance. So we already have practice with that. Subscripts indicate the number of atoms. The subscripts are the atom ratio. If there is only one atom to an element, then the subscript is omitted. Yeah, if there's only one oxygen, you don't need to write 1. It's a 2-to-1 ratio. We don't write the 1. That's what that's saying. So what's this called here? Let's cover that up. This one. NAs. So would this be sodium mononitrogen trioxide? Sodium mononitrogen trioxide. No, we don't use the mono and the tri for anything more than 2 atoms. Not only that, it has to be a binary molecular compound to use that. In fact, you should be able to recognize this. NO3 is called nitrate, so this is sodium nitrate. Sodium nitrate. Sodium nitrate indicates we have 1 atom of sodium, 1 atom of nitrogen, and 3 atoms of oxygen. That's the atom ratio. This is not the mass ratio. The mass ratio is different. The problem is this. Let's say I need a certain amount of sodium nitrate. Is there a machine that tells me how many atoms of sodium and how many atoms of nitrogen and how many atoms of oxygen I have? Let's say I need to weigh out normally when we get a sample of sodium nitrate, we weigh it out. We get some number of grams of it, right? We get, let's say I'll get a kilogram of sodium nitrate, or I'll get a gram of sodium nitrate, or I'll get a pound of sodium nitrate, right? But there's that disconnect. The disconnect is when we want some sodium nitrate, we got to weigh it out. So we're doing this mass stuff, you know. But when we think about sodium nitrate, I don't want to deal with mass, you know. I'd much rather just deal with the atoms. You know, how many atoms of each I'm going to have. Do that. And so what we have to do is we have to make a connection between the mass and the atom ratio, which we can. And so there are different ways we can do that connection, which we'll talk about in this chapter. And so even though these are the 2 most common, we have to interrelate them. So this is a composition based on atom composition. Okay, how many atoms of each element are in the formula unit of ammonium carbonate? So ammonium carbonate, well, we know it's an ionic compound, ammonium ions and carbonate ions. So first off, ammonium, you just have to drill that down. Does somebody have it drilled down? What is it?
NH4+.
Oh, good. That's good. NH4 plus. And then carbonate. What is carbonate? See, is it 3 or you have a choice? Is 3 oxygen or 4 oxygen? 3 oxygen. And what is borate's charge? 3, therefore carbonate is 2. Yeah. So this is CO3. On the video we talked about this. Let's see it here. Nomenclature is a lot of memorization, so your homework should be to memorize this stuff. You know, however you memorize things, just memorize it. You know, I have a different routine for memorizing this. You might not like it. A lot of people don't like it, actually. They have their own method, which is fine. I don't really care which method you use, just memorize it. Okay, borate is 3 oxygen or 4 oxygen? 3. And the charge? 3 minus, therefore carbonate is 3 oxygen, 2 charge. So that's easy. It should be easy. Okay, how many ammoniums, how many carbonates?
2 ammonium.
2 ammoniums. And how many carbonates? 1 carbonate. Okay, so that's ammonium carbonate. Okay, let's break down the composition of ammonium carbonate next. Atom by atom. I think that's what they want. So let's do this slideshow. Next slide. How many atoms of each element are in a formula unit? Well, what is a formula unit again? Somebody explain it to me in their own words. Formula unit. If I use the jargon in class, if you don't know the definition, just look it up in glossary or dictionary or something like that, or Wikipedia. But make sure you know it before the test. What the formula unit is. Well, formula unit is just this one unit, the simplest unit. So one formula unit of this would be 2 ammonium ions and 1 carbonate ion. 2 ammonium ions and 1 carbonate ion. Okay. In one formula unit of this, how many nitrogens do we have? We have 2 nitrogens. And how many hydrogens do we have? 8 hydrogens. Carbon,
One.
1 carbon and 3 oxygens. So that wasn't so bad. They have this weird thing, you know. For me, it's fine. I don't. Maybe to them, it's not weird. In my system, very weird. But they do it based on the acid. You know, they have you memorize all the acids and then work backwards, which is good. Sure. Yeah. Now here's the final answer: 2 nitrogens, 8 hydrogens, 1 carbon, and 3 oxygens. What is the formula unit of water? H2O, 1 water molecule. What is the formula unit of sodium chloride? Would it be 1 molecule of sodium chloride? It would be 1 sodium ion and 1 chloride ion, but we wouldn't call it a molecule. Would you call this a molecule of ammonium carbonate? Ionic compounds don't form molecules. Ionic compounds form, say, lattices. Molecular compounds form molecules. And so what's the difference? Well, the structure is different. And so if we look at the ammonium carbonate structure, crystal structure, you can see how things are arranged in the lattice. Ammonium carbonate. Should have gotten some crystal structures earlier. Basically, what you can see here, you know, we just pack together. This is ammonium carbonate would be kind of similar to this, where we pack together ammonium ions and carbonate ions. It's not ammonium carbonate. Look, it will take me a few minutes to find it, but the ammonium ions look like this, right here. One of the hydrogens cut off. They're kind of ball-shaped ammonium ions. Carbonate ions. This is ammonium carbonate, by the way. Carbonate ions look like this, triangular thing. So when you pack those together, packed together in an interesting way. But unfortunately, that's not the lattice there. Find it. But anyway, it doesn't form molecules. The ions just packed together in a lattice like that. So the formula unit is just the simplest, you know, the simplest unit. There are lots of ions here. The simplest unit would be one of these and one of these, you know, or 2 of these and one of those, or 2 of those and one of these. That would be the simplest unit. So that's it. For molecules, though, we have molecules, discrete molecules. Right? Now, how do you recognize a molecular compound from a ionic compound? What did I say last week? How do you recognize if something's molecular or something's ionic? It's not always monotone. Ionic compounds are always going to have, well, I give a simple one. It has to do with what type of element we're dealing with. Metal and non-metal. Ionic compounds are metals and non-metals, whereas molecular compounds are all non-metals. Now this is the tricky one because this is all non-metals, but this is an ionic compound. How you'd be able to tell is because we know ammonium. We should be able to recognize it right off, and then carbonate. So we see that this is ammonium carbonate versus some other molecular compounds that definitely don't consist of ions, like nitrous oxide. You know, you look at nitrous oxide. This is all non-metals too, but we don't see ions there necessarily, you know, when we're looking at ions that we typically recognize. And so this is this is one of the exceptions. This is all non-metals, but this is ionic compound. Another common one is ammonium nitrate. Ammonium nitrate, this is all non-metals, but this is an ionic compound. Because it consists of the ammonium ion and the nitrate ion. And so there, the formula unit would just represent one ion each. Whereas in the molecular compound, the formula unit usually refers to the molecule itself. Okay, so when we're referring to the molecular mass, what are they talking about? When we're referring to the molecular mass, this is the mass of an individual molecule. It could be the average, or it could be the specific mass. You know, molecular mass is just the mass of the molecule. If you're taking the average molecule, then it's going to be the average mass. If you're looking at a specific molecule, let's say H1, H3, H1, H3, it's going to have a different mass. And we can calculate that mass if we know the isotopic mass is. And so, anyway, the molecular mass, this is typically the average mass of the molecule, the compound expressed in atomic mass units. The formula mass, well, not everything forms molecules, right? The formula mass is the general all-purpose term. It's like the formula unit. Is the formula unit okay to use for ionic compounds? Yes, the word formula unit. Is formula unit okay to use for molecular compounds? Yes. We could use formula unit for anything. However, we cannot use molecular unit for, can we use molecular unit for ionic compounds? No, we can't, because molecules don't form ionic compounds. And so this one is a little bit more restricted. This is more general. We use formula mass for everything. And so if you buy a chemical, it says formula mass. They aren't going to write molecular mass, so they'll just write formula mass and use it for everything. And so this is, formula mass is just the mass of a formula unit. Well, that's what we did. We got what was the molecular mass of water? 18.02 U. What's the formula mass for water? 18.02 U. If we wanted to figure out do we say what is the molecular mass of ammonium carbonate? Would we say that? No. Instead, we should say what is the formula mass? Okay, what is the formula mass? Oh, I have two nitrogens. Each nitrogen, and we'll do this as we go along, 14.01 U. We usually go to 2 decimal places. I have 8 hydrogens, 8.01 U. I have 1 carbon. Carbon is, the average is 1201 U. That's the average. 3 oxygens, 3 times 16.00 U. And so what I could do is I could figure out what the formula mass is by just adding up or summing up all the masses of the atoms. So that's going to give me the formula mass here. And again, this is not the molecular mass. It's not the molecular mass because this doesn't form molecules. And then I could get the percent nitrogen, the percent hydrogen, the percent carbon, and the percent oxygen. All 4 of those percentages should add up to 100%.
Why is hydrogen 8 times 8.01?
It's just because I made a mistake. 101. And so 2 times 1401 gives us 2802. 8 times 101 gives us 808. This is going to be 1201. And then 3 times 16 is 3248. It's 48. And so we can calculate, I can calculate these quite quickly because I have them memorized, a lot of these memorized. So this is 10, 11, and then 16, 18, 24, and then 4, 8, 9, 94, 11 U. And so one formula unit of this weighs 94.11 U on average. What would be it? And so this is, and then we can calculate the percent. If I want the percent nitrogen, how would I set up the calculation? Percent nitrogen would be by mass. By atom, it would be, what is the percent nitrogen by atom? It'd be 2 atoms of nitrogen over how many total atoms? 14. 2 out of 14 would be nitrogen. 8 out of 14 would be hydrogen. 1 out of 14 carbon and 3 out of, so for sure the biggest percent by atom would be hydrogen, but not by mass. Hydrogen doesn't weigh much, so the percent by mass, to set up the percent by mass nitrogen, we do the mass of nitrogen, 28.02 U, over the total, times 100. We can do that for each of the 4. Here we are. This is CO2. That's the formula mass or the molecular mass. Since CO2 forms molecules, this is the formula mass or molecular mass of CO2. So we got two oxygens at 16 OU and 1 carbon at 12 OU. So this 32 plus 12 is 44, 4401 U. That's how much a molecule. The average CO2 molecule weighs how much it would be. There might not be anything, there might not be such thing as an average, you know. It's like, it's like if you have two $10 bills and one $20 bill, you know, what's the average? Two $10 bills and one $20 bill, then the average is going to be closer to something. Well, you probably get the sum, but you might not have that denomination. Calculate. That's probably not the good analogy for that. Calculate the formula mass for ammonium nitrate. So what is the formula of ammonium nitrate first? So for ammonium, we said is NH4 plus. What is nitrate? NO3 minus. Good. So we have NH4 plus and NO3 minus. And so how many of each do we need? 1 of each. So the formula is just going to be NH4 NO3. All right, so what we want to do is we want to calculate the formula mass for this. So what we have to figure out is how many atoms of each element we have in there. And so how many atoms of nitrogen? 2 nitrogens. This is tricky. A lot of people say 1, but they're split up here. So we got 2 nitrogen. That's 2 times, what is the average? 1401 U is the average for nitrogen. 1401 U, that gives us 28.02. So altogether, I have 28.02 U's worth of nitrogen atoms in this formula unit. How many hydrogens do I have? 4 hydrogens. Now 4 times 101 gives us 404 U, total hydrogen. And then 3 oxygens, 3 times 16, OU. 3 times 16 is 48. OU. So we can add this up. 2 and 4, 6, 0, 0, 0, 12, and that's 10, and then 3 and 4, 7. 70.06 U. So one formula unit of this, NH4NO3, weighs 70.06 U. And so what we could say is this. We could say that there's 70.06. This is what we do. We're going to be using these as conversion factors eventually. So what we can say is there's 70.06 U's worth of ammonium nitrate for every ammonium nitrate, for 1 ammonium nitrate formula unit. Formula unit, we'll just abbreviate. For 1 ammonium nitrate formula unit. So, oh, I misadded, sorry. 80.
I got 80.06.
80.06, sorry. That's my fault. 80.06. 80.06, which means they got 0.05. And so what's the problem that I had? Which one is more accurate? Looking at their numbers and looking at my numbers, which one do you think is more accurate? Theirs or mine? Theirs is more accurate. Theirs is more accurate, but you know speed counts. And when you're doing these things, the easiest thing to do is just go 2 decimals, and then you can do it rapidly. If you go 3 decimals, you're gonna slow yourself down. 2 decimals is usually enough because that gives us 4 to 6 figs. If we go 3 decimals, we should go 3 decimals all the way through. Because no, they rounded nitrogen to 2 decimals, and I don't know what they're doing with oxygen. They really screwed up oxygen. But they rounded it to 2 decimals. So why did they round 2, 2, and 3? They rounded it because they wanted everybody to use the same hydrogen, 108 for everything. But, so I don't know, whatever you'd like to do, you could just keep it as 108, or you can memorize 2. But theirs is more accurate. Now how often, when you go weigh something, is there a balance that weighs in U? Is there a balance that weighs in U? No, our balance is weighed in grams, right? That's what our balance is weighing. Our balance is weighed in grams. And I told you this number before. I don't know if anybody remembers this number. But in 1 gram, how many U are there? In 1 gram, how many U are there? Just approximately. Does anybody remember that? Did anybody write it down? You remember that? Yeah. 6.022 times 10 to the 23rd U in 1 gram. That number turns out to be easy to remember because it's a common number that we use. But you know, this is like 602, what is it, trillion, billion, or something like that. A billion, trillion, 602 million trillion. What was that? I forgot, but we can figure it out. It would be 602.2 times 10 to the, so we make this number bigger, we make this smaller. It would be 10 to the 21st. And so we get, what is a trillion? A trillion is 10 to the 6th a billion, million, 10 to the 9th is billion, 10 to the 12th. So let's do this. We'll go 10 to the 12th, which is a billion, or trillion. Trillion. So 10 to the 12th, and then we need another 10 to the, add up to that. Add up to that. 19, 9. We need 9. And so 10 to the 9th is a billion. 10 to the 12th is a trillion. So 10 to the 9th times 10 to the 12th gives us 10 to the 21st, correct? And so this would be 602 billion trillion U in 1 gram. Where did that number come from? I mean, where did that number come from? This number came from, this comes from the definition of the U. One, it comes from the definition of the U, and 2, something called the mole. Definition of the mole. So we'll talk about next. But what is the definition of the U? How's the U defined? Is there a 1 U mass locked away in some vault in France? So if they don't have a 1 U mass locked away in France, maybe they have a 1 kilo U mass locked away in France, like a kilogram mass. Do they have a 6.022 times 10 to the 21st U mass locked away in France? No, actually, they don't have anything locked away in France because the U is accessible to everyone. It's the people's. It's readily available and it's cheap. So how is it defined? How's the U defined again? You guys got to think. You know, the more days away. You know, because I guess we talked about what last week before. You know, the more days, the more that memory fades. The more trouble you're going to be in for the test. And so you want to, you know, keep it fresh as you can. Just, you know, okay, what is it related to? You don't have to tell me what is defined or how it's defined. Just what is it related to? Yeah, carbon. So that's good. Can anybody be a little bit more specific? Carbon 12. Yeah, it's related to carbon 12. So that's, if you know at least it's related to carbon 12, then on multiple choice you'd be better off. If you don't even know it's related to carbon 12, that's a means you should review. You should review a lot more. Well, it's not defined by 1U, it's defined by 12U. 12U is the mass of the carbon 12 atom. So a single atom, carbon 12, weighs exactly 12U. Now, we have something called the mole, which is here, MOL. The mole has a definition that's based on carbon 12 as well. And the mole is this. The mole is the number of carbon 12 atoms in exactly 12 grams of carbon 12. So if I take exactly 12 grams of carbon 12, approximately how many atoms are there? So in exactly 12 grams of carbon 12, there are approximately 6.022 times 10 to the 23rd atoms of carbon 12. Okay, that's something that you can calculate or determine by. But this is only good to 4 sig figs. So the reason it was defined in this way is so that we would have a reasonable counting unit. You know, the mole is a counting unit. You know, for example, if you had let's say you had 36 eggs. In 36 eggs, you could just call it 36 eggs, right? Or you could call it. You have 36 eggs, you could call it 3 dozen eggs. So 36 eggs, 3 dozen eggs, you know, it doesn't matter. You could use either. So if you had let's say 120 eggs, you could call it 120 eggs, or 120 eggs would be 10 dozen eggs. What if you had 6.022 times 10 to the 23rd eggs? What would you call it? So that's what we could call it. 6.022 times 10 to the 23rd. And then we know that there's 1 dozen is equivalent to 12, so divided by 12. We would call it 5.018 times 10 to the 22nd dozen eggs. Right? so is a dozen a very useful counting unit for eggs? Yeah, but is a lot of eggs? No. Now, when we're dealing with atoms, 12 grams of carbon is not that much. 12 grams of carbon is like, well, the carbon's about maybe about 2 grams per milliliter, so it's about 6 milliliters worth of carbon. Is that much? 6 cubic centimeters worth of carbon? Actually, what is the density of diamond? I don't know that number offhand, but I'm kind of interested in the density of diamond. 3.5. 3. So if I have 12 grams, that'd be like 4 cubic centimeters worth of diamonds, let's say. That's 12 grams of carbon 12. That's not that much, you know. We're talking about like 4 milliliters, 6 milliliters, depends what it is. Graphite's going to be less than. But we're talking about a huge number of atoms. And so this is a new counting unit. 6.022 times 10 to the 23rd of anything is a mole. 6.022 times 10 to the 23rd of anything is what we call a mole. Defined, this is to forcing things. Defined as 1 mole. Or 1 mol for sure. And so it's kind of weird. We have 1 mole of U for every gram. This one a lot of people don't use that much. But the way, why did they pick such an odd number here? Why didn't they keep it simple? Why didn't they just say 1 times 10 to the 20th of anything is a mole? Because that would bring us to, gram quantities. And so if we did like 1 times 10 to the 20th or 1 times 10 to the 25th, that's a lot easier number to remember. And so why did they pick such an odd number? Does somebody know why they picked such an odd number? Well, they didn't really pick an odd number. That's the odd number that came out by this. So why did they define it like this? The reason that this number came out weird, and the reason they defined it in this way is that we'll have this interesting number relationship. That is, how much does a carbon-12 atom weigh? It weighs exactly 12 U. And so I can come up with this conversion factor, 12 U's worth of carbon-12 for every carbon-12 atom. If I have 1 mole of carbon-12 atoms, how much does it weigh? 1 mole of carbon-12 atoms weighs exactly 12 grams. And so an interesting relationship comes here. I have 12 grams of carbon-12 for every mole of carbon-12 atoms. And so this is the mass relationship. The number is the same. And so the mass can be U per formula unit or grams per mole of formula units. And numerically, they're the same number. And so it's much more versatile. If we define it in this strange way, then we get this number relationship that works. And so what we can do is this. Quite simply. How much does a water molecule weigh? Yeah. And so it's going to be 18.02 U's worth of H2O per H2O molecule, or formula unit, use that. Or we could say 18.02 grams of water for every mole of H2O molecule. Now, how many molecules is a mole? Well, a mole, it's like a dozen kind of thing, but it's a weird number. It's 6.022 times 10 to the 23rd molecules. So if I have 6.022 times 10 to the 23rd molecules, this is going to weigh 18.02 grams. And so mole quantities are, for us, if we're using U, then we need to know the specific isotope that we're dealing with. This number is a special number. This is called Avogadro's number. Avogadro's. Look at it, they spell Avogadro's or Avogadro. What do you think it is? Avo? Or Avo? It's Avogadro's number. Avogadro's number gets the symbol N, capital N sub A. Avogadro's. They have it to 3 sig figs, but we need it to 4 sig figs. And let's see how they define it. They define it as the amount of any substance that contains the same number of units as the number of atoms in carbon 12, in 12 grams of carbon 12. So if I have 0.25 moles of ammonia, how many molecules is that? If I have a quarter mole, then it's going to be a quarter of the. So we have one more conversion factor. The one more conversion factor is this. There's 6.022 times 10 to the 23rd of anything per mole of that anything. So if I have 0.25 moles of ammonia, what's the formula for ammonia? NH3. Then there are 6.022 times 10 to the 23rd ammonia molecules per mole of ammonia molecules. And we can get it. Just be 1/4 of that. All right, we'll take a break now. Start up again.